Hey everybody. So for this first slide, we're going to talk about the very first topic of this class, which is statics. Now, one thing I want to note is I'm going to try to split this into multiple parts. So this first video is all going to be about static equilibrium. So in the previous science classes that you've taken, you should have learned about the concept of equilibrium. It's a huge, major thing that pretty much all of science and physics is based off of. So for those who don't remember or just want a quick refresher, equilibrium is that state for an object when it's either at rest or moving at a constant linear velocity. This comes from Newton's second law, basically saying that all the forces must add up to zero. Well, I guess Newton's first and second law. So this gives us our very first condition for equilibrium, that all the forces on an object must add up to zero. So if we add up all the forces in the x direction, it adds up to zero. All the forces in the y adds up to zero, and all the forces in the z direction add up to zero, and so on and so on. This is the first condition. This is the one that we typically use whenever we think of and we do things dealing with equilibrium. Now, there actually ends up being a second condition because there are cases where an object could technically be moving in a nonlinear way or at a non-constant way and yet not be translationally moving. So we have to actually consider a second condition, which is that all the torques also must add up to zero. Now you should have learned about torques in the previous class, but we're going to do a very quick refresher here. So torque, the equation is Fr sine theta. This is the one that we're going to be using. So basically the torque is related to the rotation caused by a force. I always think of it as the rotational force, if you will. So the equation is Fr sine theta. F is the magnitude of the force being applied onto the object. R is the distance that force is applied from the pivot. Whenever you have an object that can rotate, you have a location that's called the pivot point. So R is that distance from the force to the pivot. And theta is the angle between the force and radially from the pivot. Basically what that means is that if we connect a straight line going from the pivot to the force, that angle between them is going to be the theta. All right, so we end up having situations like this. So if our force is at an angle, we have to use Fr sine theta. Now, one of the shortcuts that we can do is a lot of times we're going to be dealing with cases where we have the forces completely perpendicular to the beam, in which case we could just simplify it to our Fr and drop the whole sine theta. Another thing we could do is a lot of times if we do have things at an angle, sometimes we just want to know what the y component is. So we can replace the f sine theta part with essentially y component of the force times r. That's pretty much what this down here is trying to say, is that it's the distance times the y component of the tension, as opposed to here being all linked together. Now there are a few things that that you should note right away about torque. I'll be mentioning more as we continue with the slides. But the first thing is that the force that acts at a pivot exerts no torque. Now that doesn't mean that the force doesn't exist. It just means it doesn't exert a torque. Now that's extremely important because that allows us to realize that anytime we have a pivot at a location, any force that's there has no torque. This helps simplify a lot of our torque equations when we start doing some of the torques. Now, to kind of piggyback with that, this becomes extremely important when we add in the fact that when we deal with equilibrium, pretty much every question we're doing in this topic, we can choose the location of our pivot. You'll see this later on, that this makes our problems a lot easier, because we can pick points where we can say, hey, there's a force here that I don't know, and it's going to mess up my problem. So you could place a pivot at that location, and we no longer have to consider the torque from that force. So this becomes extremely helpful for us. Another thing is that we want to keep track of rotation and signs. We'll get to that in a second. And then another thing is sometimes you'll be told that the object, like the beam that you're dealing with, that's going to end up rotating, that has all the forces acting on it. Sometimes it has no mass, so you don't have to worry about it, but other times they will tell you that it has a mass. And when it says that it has a uniform mass, that it's a uniform object, that means the center of its mass, basically the location where all of its weight is located, is always going to be in the very middle of that object. Again, you'll see some examples of this later on. Now, one thing that I want to note is that want to remind you is that you want to make sure that you're trying to use some of the torque equations. It's an extremely powerful equation. A lot of people, for some reason, feel like they can get away with some of the forces, and there are some cases where you can just do some of the forces and answer the problem. However, it becomes extremely important when you have cases where maybe you don't have all the information to do some of the forces. For example, let's say you're missing 2 vertical forces. You can't do some of the forces if you're missing 2 pieces of information. Some of the torques helps that. With these 2 points, that no torque at the pivot and choose your pivot, this helps us get rid of that other unknown force. Also, anytime we are dealing with trying to figure out a location of a force, that also hints to torque. I usually recommend that when you're doing problems in this topic, that you should first consider, can I do some of the torques? So this first problem, what we're going to do is we're just going to practice this, and it's all about some of the forces. So we have a chandelier supported by ropes, and we want to know FA and FB. So you can pause this video and practice yourself, and we'll go over it in a second. All right. So our very first step when doing anything with forces and torques is we have to draw an FBD. So for those who don't know, FBD is a free body diagram or a force body diagram. Basically, it's a drawing of all the forces acting on the object. So I have a box for right in the middle of these 3 wires. I have the weight of the chandelier pulling down. I have FB pulling it to the right, and then I have FA pulling it at an angle. I can't deal with an angled vector and 2 perpendicular vectors, so I have to break FA into a vertical and horizontal component. And now that I have my diagram, I can now use my equilibrium equations. So I use my sum of the forces. I can do sum of the forces in the x direction have to be equal to 0. So they're in opposite directions. So FB equals FAX. So once I find this, I found FB. And then I can use sum of the forces in the y direction. So FG equals FAY because once again, they're in opposite directions since there's no other forces. Now I know what FG is. It's mass times gravity, 200 times 9.8 or 1960 newtons. So I know that the vertical component is 1960 newtons. Well, now that I have that number, I can use trig. The y component is equal to the vector times sine theta. I know that the angle is 60 degrees, so plug in the 1960 from before, divide by sine 60, and I get 2263 newtons. So that is what FA is equal to. Now I need to figure out what FB is. Well, going back to the previous equation we had, we knew that the horizontal component was equal to FB. So if I take this and times by cosine of 60, I'll end up getting the x component of the force, which is just FB. All right, so that's how we would use some of the forces. Again, pretty standard, straight from before. Now we'll do a little practice with some of the torques. Now, here we have a boulder that's going to be lifted up by a person. The person's going to push down, and the boulder has some weight pushing down, and they give us some numbers. So what you can do is pause this really quick. Now you're going to be using some of the torques. We'll go over this in a second. Now, you cannot do some of the forces here because even though you see that there are 2 forces drawn here, there is a third force that's not drawn, and usually in a lot of these diagrams, it won't normally be drawn. There's a force coming from the pivot because this is a normal force. It's something touching a surface. So there's actually a third unknown force. If we try to do sum of the forces, I know what this force is, but I'd have 1 and 2 unknowns. So I can't do that. I have to do sum of the torques. Now, if you remember, I had made a comment that you want to be careful with direction. My pivot is located right here. So I'm going to place that pivot there, which makes sense because, as I said, there is a normal force that I don't know anything about right at that location. So I want the pivot here to get rid of it, so there's no torque from there. So I can just focus on this torque and this torque. Now, the other thing that I want to pay attention for is direction. With forces, it's easy. Up is positive, down is negative, or vice versa. Here, though, what we talk about is the direction being clockwise or counterclockwise. So if my pivot's at this location, pushing down on this side is going to cause the whole thing to go clockwise. While over here, having the pivot at this location and pushing down on this side would make it go counterclockwise. If you're having trouble visualizing this, take your pencil, place your finger in the middle and have that act as the pivot, and then push on the right, down on the right side and push down on the left side. You'll see that the one on the right causes it to go clockwise, the one on the left causes it to go counterclockwise. So what we're going to say is this is a positive, this one's the positive and this one's the negative, but it doesn't really matter which one's which. So here my sum of the torques, the force times distance, and I'm going to set that equal to the force times distance from this one. So the torque of the boulder is equal to the torque of the person. Moving things around and plugging the numbers in for the masses and distances, I end up getting that the person is exerting a force of 980 newtons, essentially about 1,000 newtons. So going back to the numbers that get plugged into here, so I know that the distance from the boulder to the pivot is 1 meter and the whole rod is 3 meters. So that means that this distance has to be 2 meters. Now, this becomes extremely important. This is actually why levers like this are considered simple machines and why they're so important for civilization, because this results in what's called mechanical advantage. If I want to lift this boulder up, I would have to exert about 2,000 newtons of force. However, using this lever, I only have to exert 1,000 newton force to lift it. Now, there are some caveats, like it requires just as much work to lift it with the lever versus lifting it up, mainly because even though the force is lower, it's over a longer distance. But we're not going to touch energy in this topic. So this actually becomes an extremely important thing. Anyone who's ever done anything, any physical labor, should have realized that if they have to rotate something, having a longer object helps. I remember at one of my jobs, one of the things that we had to do was in the morning we would have to go to a valve that gas was flowing in, and we'd have to rotate this little insert so that gas can flow through. And then at night, we would have to close it and rotate it back. At one point, someone lost the wrench that went with it. So we had to use this really small wrench, a very small distance. Because of that, in order to rotate it, we would have to exert significantly more force, and it took us a lot harder. In fact, there were some people who didn't have the strength to do it. But then we're lucky enough to actually find a much bigger wrench later on, and then it became a joke. Everyone was able to rotate it with ease. So longer levers result in an easier rotation. All right, so this is given in your textbook. Basically, it's everything that I just mentioned about how you break down these problems. The first thing that you want to do is draw an FBD. You want to make sure that you draw all of the forces that are acting on it, their direction, and their locations. It becomes extremely important that you're able to do this. Now, you'll notice that in a lot of the questions we are doing here, I'm giving you the FPDs. They're right there. What you can do if you want is just cover the diagram and try to draw the FPD yourself so that you get practice. But it is extremely important that you're able to do that. Now, step 2 basically says to set up a coordinate system. This is basically referring to stating whether or not up, down, left, right, clockwise, counterclockwise, what direction's positive, what direction's negative, and making sure that you're consistent throughout. And then 3 and 4 kind of together is that basically you're setting up your conditions for equilibrium. You're doing sum of the forces and then sum of the torques. Now you can feel free to start off with sum of the forces. That's fine. Typically outside of this class, that's what you would normally do. However, I would recommend starting with sum of the torques. The reason being, like I said, most people for some reason feel like it's not necessary, but I can guarantee that if you're doing a problem in this class, it's most likely going to require at least one torque equation. So you're going to have to do some of the torques. And then you use them to solve the number of unknowns. And that's pretty much it. It says here that you have a max of 3 unknowns. 3 equations, 3 unknowns. All right, so here's another question where we have two children on a seesaw, and you have to figure out the distance of child B and then the value of Fn. So pause this video, you can work on it, and we'll go over it in a second. All right, so for the first part, figuring out where child B is, what I want to do is I'm looking at this FBD. This FBD works for both scenarios. And what I'm going to do is, once again, I don't know the distance where this person is. I need to figure out where my pivot is, and I'll put it right here where the actual pivot is because there's this unknown normal force that I don't know about. So I don't want to deal with it right now, so I'm going to put the pivot here. You'll see later on that we can put the pivot wherever we want as long as we have enough values. So we set up our torque. So starting from the left side, we have a torque that's going to cause, based off the pivot here, it's going to cause it to rotate counterclockwise. So F times R minus the torque from this side because it's going to go clockwise. They go in different directions. So we end up getting that the torque of child A equals the torque of child B. A lot of times once you get into the hang of this, you probably just jump straight to this part. But for now, let's start off with writing this first line. So we have this set up. We have all the values, and we can solve for x. So we have the child, the other girl, both children, and the distance of child A. That gives us that x has to be 3 meters. Interesting thing, the numbers have a little bit of a symmetry. Mass is 30 kilograms, the distance is 3. Mass is 25, distance is 2.5. Some of you may have noticed that and probably guessed that it might have been 3. But again, on a test and on homeworks, I need to see the work. So we have this, and that's good. Now on to part B. On to part B, we're looking for the normal force. Well, I can actually do some of the forces now. Before I couldn't because some of the forces wouldn't tell me location. But now I have 1, 2, 3 pieces of information. I can find Fn. It's the only unknown. So the force of the normal force pointed up is equal to the 3 forces going down. Plug in the numbers in, and I get that Fn is equal to 735 newtons. All right, now I want to show something real quick that I could do the same thing by placing, by placing the pivot where child B is. And I'd end up with the same value. So do my thing of the sum of the torques. Please forgive my handwriting, I'm on a mouse. So here's my pivot. This force exerts no torque, so I'm going to skip it. I have Fn here. Fn is going to cause it to go clockwise. So I'm going to have Fn times 3 meters. And then I have the center of mass of the beam. So it's going to be minus, since this is going to cause it to go counterclockwise, minus 196 times 3. And then FA, also going to cause it to go counterclockwise. So that's going to be another minus 294 times 5.5. And all this is going to be equal to 0. So when I plug these numbers in, 196 times 3 and 294 times 5.5, I end up getting 3 times Fn equals 2205, which then gets me that the normal force is going to be 735. So the exact same number I got before. Again, maybe some slight differences because of the 9.8s and stuff, but essentially everything's there. So, like I said, no matter how you do it, wherever you put your pivot, you'll still get the numbers as long as you're being consistent and you have enough information. All right, now let's work on this one. So here we have a muscle, a person holding a ball, and they're trying to figure out the force of the muscle. So work on that. You can pause this video to work on the problem yourself, and we'll go over it in a second. All right, so once again, we can't do some of the forces because we have 2 unknowns, and that's too many. So now we're going to do some of the torques. I'm looking for FM, but I don't know anything about the joint, this FJ, which is the joint force. So I'm going to place my pivot at this location so that I don't have to worry about this torque. And I'll only have to worry about the torque of 1, 2, 3 objects. So some of the torques, first of the muscle, so its distance times its force, that's a counterclockwise force, counterclockwise torque. The center of gravity, which is a clockwise torque, minus that. And then this ball giving another clockwise torque. Plugging all these things in, solving for FM, moving everything to the side, we end up getting that it's 402 newtons. So the muscle is going to exert a little bit over 400 newtons. Now, part B is actually extremely interesting. The main thing is this. When we do this, now that it's going to be at an angle, there's now an angle between the force and the beam, I now have to do FR sine theta. So essentially what I'm doing is I'm taking that torque equation, the FR, and I'm going to multiply it by a trig function. Now I know I'm using cosine 45. I'll explain that in a second, but you'll notice that it doesn't even matter. So we end up having the same thing. Here we have the cosine 45, but each one, because they're all vertical forces, all acting at the same angle, we end up finding out that they just cancel out, which means that the force of the muscle is still 400 newtons. So it turns out it doesn't really matter what the angle is because it's all being consistent. The force of the muscle doesn't change. Now, to kind of explain a little bit why I was using cosine 45, it's mainly because of the fact that this angle is pretty much a horizontal angle, but the forces are acting vertically on the object. Now, to kind of explain it a little bit better, I have a very crude drawing here. So this is the force of the muscle. This is the angle. Now, to make it a little bit clear why I did cosine 45, I'm going to change the angle to 35. Now, if you look here, as I said before, the angle that we use in the sine theta is the angle between the force and the beam, which is this location. So this arrow is pointing to where theta is. So that means in this case, this would be 55 degrees. So when I set up my equation, I would do sine of 55 degrees. But because of trig identity, sine of 55 degrees is also equal to cosine 35. This is a little trick that, again, when you have enough practice, you'll start to realize some of this stuff. But, for now, if if you wanted to just do sine 45 and do the trig to figure out, what the vertical, basically this vertical angle is from the force to the beam, go right ahead. You don't have to do this. Each person solves their problem slightly differently. All right. Now, moving on to this question. So this is a very common question, pretty much a signpost, I guess, where we're going to try to figure out what the tension force is and the components of the hinge force. That's what FHY and FHX is. Two things to note. One, even though I'm asking for it in this order, you do not need to solve it in this order. You might actually find it easier to solve in reverse order. The other thing that I want to point out is that the angle of this is not the same as the angle of the hinge. So the angle that this cable is acting at is not the same as the angle that the hinge acts at. So with those two things, pause the video and we'll go over it in a second. Okay, so what we're going to do is, if I try to do some of the forces, again, I come up empty-handed. I have nothing in the horizontal direction, and I have two unknowns in the vertical direction. So, sum the torques. Now, it doesn't matter where I put the pivot. I could put the pivot here, and then find basically find this value, this vertical tension, or I could put the pivot over here, and I can find the vertical component of the hinge. Either way, it doesn't change the work. All it changes is the order of what I find stuff. So you can actually try this out at home and see that it doesn't matter. You'll still get the same vertical components regardless. So what I'm going to do is I'm going to set the pivot at this hinge, and then I'm going to go to the side. There's no torque caused by these forces, so I'm going to this first force. So the torque, which is clockwise, is going to be mg times its distance, half of the beam, that's where its center of mass is. Continuing on, I have the sine also pulling it clockwise, so I get another negative torque, mg 2.2 meters, and then I have the vertical component of the tension being 2.2 meters. Now, the reason I'm not doing the FR sine theta here is just because I'm going to need to find this vertical component anyway, so might as well make my life easy right now. So take this equation, move everything around, simplify things, and I end up getting that the vertical component is a little bit under 400 newtons. With that, and knowing that this acts at an angle of 30 degrees, I can now find Ft, the tension force, and I can find it to be a little bit under 800 newtons. All right, so far so good. Now what I can do is I can find, now that I have these two pieces, I could use the third trig identity to find the horizontal component. Now, I probably should write this. I don't end up writing it, but I know right from just looking at this that this horizontal tension has to be equal to this horizontal hinge. So when I use this trig identity to find the horizontal tension, I get it's a little bit under 700, and that's the horizontal hinge. So you notice that I'm actually solving this backwards, but again, it doesn't actually matter. You could have solved it in any order you wanted. Now to find the vertical component, again, I cannot do trig because I don't know what the angle is between the horizontal and the actual hinge vector. So I have to do sum of the forces. So the two vertical components equal these two downward components. So I end up getting this. The hinge vertical component is equal to the combined weight plus the vertical tension. Moving things around and solving, I end up getting that the vertical component is 123 newtons. And that's it. Now, really quickly, if you want, you can use SOHCAHTOA to figure out what the angle is, and you'll find that it's definitely not the same as the 30 degrees for the tension. So again, huge thing to remember. that these angles are not the same. That's why it's not even labeled as theta here. Now this is the last question that we're going to do in this video. And it's another very common, very typical question that you do when it comes to equilibrium. So here's a ladder question. We have a ladder. There is friction on the bottom surface of the ladder. And we have a person walking up the ladder, and they're trying to figure out how far up the ladder can the person go before the ladder begins to slip. Again, you can pause the video, work on this yourself, and we'll go over it in a second. All right, so in all these scenarios so far, what we've done was we started with some of the torque. So let's see, if I wanted to do that same thing, I would most likely want to put my torque here at this location, since this has two forces. If I put it here, if I put my pivot here, then I only get rid of one force and I have these two forces here. So I'm going to put my pivot at this location. So the torque here is negligible. So we end up having is the torque caused by the wall, the torque caused by the center of gravity, and the torque caused by the man. That's what these three are. Now you'll notice that I'm leaving these in their variable terms for now. You'll see why I end up canceling a lot of things out, and it actually does look a little bit nicer. And we end up getting sine 70 for this, and these two act at sine 20. You can tell by the angle because this angle is taken from a vertical side. These two forces are vertical, so they're also going to be sine 20. This one's horizontal, so it's going to be the other one, the complementary angle, sine 70. So I move things around, but we have an issue. I have two unknowns. I do not know what the force from the wall is, and I don't know the location of the man. All right, no problem. I leave this equation for now, I table it, and what I'm going to do is I'm going to now go back to my other equations and use some of the forces, because maybe that first condition is going to help me. So if I look at the vertical forces, I have two knowns and one unknown. Okay, that's good. So I have that the force from the floor is going to be equal to the combined weight of the man and the ladder. Now over here, I know that there's a relationship between the force, the normal force, and the frictional force. It's mu Fn. So I can use the other sum of the forces to do the horizontal force from the friction equal to the horizontal force from the wall. And then use the mu Fn with the force from the floor in for the frictional force. So I end up getting that the force from the wall is going to be mu times the combined weight of the man and ladder. That's combining these two equations together. Now, if you want to make your life easy, you could actually plug numbers in and it'll make things a little bit easier to see. I'm just keeping it in variable terms for now. So using this and combining it with my equation I have here, what I can do is I can take this and plop it in for the force from the wall. So moving things around, I end up getting this. Now you'll notice that I actually turned the sine 70 into cosine 20 just so that they're all 20. And technically I actually could simplify this to be cotangent if I wanted to, but no point right now. So I end up having all this. And yeah, so that's what I said before. I simplified the cosine here and the sine here to get cotangent 20, and then this sine actually cancels out. So this is my simplified variable term. Plugging the numbers in that are given to me, I end up getting a value of 4.54 meters. Basically saying that the man can go up to 4.5 meters before this ladder starts to flip. Anything above 4.54 meters and the ladder slips. Anything below and it's going to be stable. All right, so that's going to be the end of this first part of the video. If you have any questions, please feel free to let me know. and I'll see you in the next video.